When you type google.com into your browser, you think you're going to google.com. You're not. You're actually going to 142.251.4.1.14. No domain name exists on the internet, only numbers. Those numbers are IP addresses, the actual addresses of servers sitting in data centers around the world. Every website you visit, every email you send, every app you open, it all routes through IP addresses. But you never type numbers, you type names. Someone has to translate the name into the number. That someone is DNS. DNS stands for Domain Name System. It's the invisible middleman that converts google.com into 142.251.41.14, so your browser knows where to actually go. The internet could have worked without DNS. You could memorize IP addresses. Type 142.251.4.1.14 directly into your browser. But that's impossible at scale. There are billions of websites. You can't remember numbers. So the internet invented DNS, a decentralized global system that translates human-readable names into machine-readable addresses in milliseconds. Understanding DNS changes how you see the internet. It's not a direct connection from your computer to a website. It's a three-step process: lookup, translation, connection. And each step reveals something about internet architecture you never knew existed. Here's what happens the moment you hit enter. After typing google.com, your browser doesn't know the IP address for google.com. So it sends a question to a DNS resolver, a server operated by your internet service provider or by a public service like Google DNS or Cloudflare DNS. That resolver is like a librarian. You ask it a question. It doesn't always know the answer, so it asks someone else. Think of it like asking for directions on the street. You need to find the Google building, but you only know its name. Step 1. You ask your local librarian. Your browser doesn't know where google.com is, so it asks your internet service provider. Think of them as your local librarian. The librarian has a desk, a phone, and a huge book of addresses. But the book doesn't have every single website in the world. It's too big. So the librarian says, I don't know where google.com is, but I know someone who does. Let me ask them. Step 2. The librarian asks the city director. The librarian calls up. This person is called the city director. They manage big buildings and important locations across the whole city. The city director says, I don't know where google.com is specifically, but I know there's a person who handles all the .com buildings. Let me give you their number. Step 3. The city director asks the .com specialist. Now the librarian calls the .com specialist. This is the person who knows the addresses of every single .com website. The .com specialist says, yes, I know google.com. It's at 142.251.41.14. Step 4. The answer comes back. The librarian receives the answer, 142.251.41.14. She tells your browser, Google is at 142.251.41.14. Your browser now knows exactly where to go. It connects directly to 142.251.41.14, and you see the Google homepage. The entire process happens in milliseconds. You never notice it. You just see the website you wanted. But here's where DNS gets smart. When the librarian looks up google.com, she doesn't just give you the answer and forget it. She writes it down in her notepad. Google.com equals 142.251.41.14. Tomorrow, when the next person asks, where is google.com? The librarian checks her notepad first. She doesn't call the city director again. She doesn't call the .com specialist again. She just says, I already know this one. It's 142.251.41.14. This notepad is called a cache, and it's why DNS is so fast. Most websites you visit, the librarian already knows the answer. She doesn't have to ask the city director. She just checks her notepad. But the notepad expires. After 24 hours, the librarian erases it and writes, okay, I need to call and verify this again. This prevents outdated information. If a website moves to a new address, the librarian eventually finds out. Now here's the really clever part. This system doesn't have a single failure point. There's not one city director. There are hundreds. They're spread across different continents. If one is asleep, another is awake. If one's phone line is down, use another. There's not one .com specialist. There are thousands. They're all connected. If one goes offline, the others still have the information. And there's not just one librarian in your city. Every city has one. Your computer connects to the nearest one. Why does this matter? Imagine if there was only one person on Earth who knew all the website addresses. If that person got sick, the entire internet would break. Every website would be unreachable. That's not a system. That's a disaster waiting to happen. Instead, DNS spreads the job across thousands of people. Different cities, different countries, different continents. If one person goes offline, thousands of others keep working. The system survives. There's another reason DNS is designed this way: proximity. Your computer connects to the nearest librarian, not a librarian on the other side of the world. That librarian connects to the nearest city director. The city director connects to the nearest .com specialist. Every connection is optimized for geography. Your request doesn't travel around the planet unnecessarily. It bounces to the closest server at each step. This is why DNS lookups happen in milliseconds, not seconds. If every DNS lookup had to travel to a central server in California, the internet would be slow. Instead, because the system is distributed, it's fast. Now imagine a DNS attack. An attacker intercepts your request and responds with a fake answer. Where is google.com? Attacker, it's at 99.99.99.99. A fake address. Your browser connects to 99.99.99.99, which is the attacker's server. You see a website that looks exactly like Google. You log in, the attacker captures your password. This is called DNS hijacking, and it's one of the most dangerous attacks on the internet. Control DNS and you control where people go. Nation-states have attempted it. Criminals exploit it regularly. ISPs have been accused of hijacking DNS to redirect traffic. If someone can intercept your DNS lookup and give you a fake answer, they can steal your credentials, redirect you to malware, or block you from visiting certain websites. This is why DNS security exists. There's a system called DNSSEC that cryptographically signs the answers. It's like the .com specialist writing their signature on the address they give you. If an attacker tries to forge that signature, you know it's fake. Large companies don't just have one address. Netflix isn't at a single IP address. Neither is Facebook or Amazon. Instead, they have thousands of servers spread across the world. When you ask where is Netflix.com, the DNS system doesn't give you one answer. It gives you the closest server to you. If you're in Singapore, you get a server in Singapore. If you're in Brazil, you get a server in Brazil. This is how Netflix stays fast everywhere. DNS routes you to the nearest copy of Netflix's system. If a server goes down in Singapore, DNS stops giving you that address. It gives you the next closest server. Your video keeps playing. You never notice the failure. This is load balancing through DNS. Companies rely on it for speed, reliability, and global distribution. Without DNS, Netflix couldn't handle millions of simultaneous viewers. Every server would be overloaded. Here's the mechanism at the core of DNS. You need to reach billions of destinations. You can't memorize billions of numbers. You can't have one person know all the answers. You can't afford slow lookups, and you can't tolerate failures. So you need a system that translates names to numbers instantly, distributes the translation work across thousands of servers, caches results locally so you don't ask twice, routes you to the closest server for speed, and fails gracefully if some servers go down. DNS solves all five with one architecture. That architecture is invisible. You type a name, you get a website. The entire lookup chain happens behind the scenes. The genius of DNS is that it's completely invisible. You type google.com, you get Google. You never see the librarian, you never see the city director, you never see the .com specialist, you never see the cache, you never see the security checks. This invisibility is intentional. DNS is infrastructure. It's supposed to be boring, reliable, and automatic. But now you know what's happening behind the scenes. Every website you visit, DNS, is translating the name you typed into the address your browser needs. The next time you type google.com, you know the truth. You're not going to google.com. You're going to 142.251.41.14. But first, your browser asked a chain of helpers across the planet where that IP address lives. They checked their notepads. They passed the question along. They found the answer in milliseconds. That invisible chain? That's DNS. And it's running billions of times every single day, every single second, keeping the internet pointing in the right direction. It's the reason the internet works at all. But here's the problem DNS doesn't solve. Once your browser connects to 142.251.41.14, how do you know it's actually Google? How do you know someone didn't intercept that connection and steal your password? That's where our next mechanism comes in. Because the internet has another invisible layer, one that locks your data with two keys, one public, one secret. And here's why that matters. If you want to understand how the internet actually protects you, subscribe now. Next week, how encryption makes it mathematically impossible for anyone to read your messages, even if they intercept them.